Okay, so now we're ready to continue this problem. We're looking at joint A. We've written in the forces acting on joint A. The displacement from joint A to E is 2i hat plus 2j hat minus 2k hat. So that would mean the unit vector from A to E is 1 over square root of 3 I hat plus j hat minus k hat. 1 over the square root of 3 is this, 0.577 to 3 significant figures. Okay, so we've got our stuff set up. We just have to set up the summation of forces there to equal 0. And force F is so summation of the forces in the x direction gives you this equation. In the y direction gives you this equation. So that would be FAB 1 over root 3 FAE minus, oh, there we go, minus 4 right over here. And then in the z direction, negative FAC, negative 1 over root 3 FAE. So FAE equals 0. From this equation, which would force FAC to equal 0 also, since this goes to 0. This goes to 0. FAB then would be the 4 kilonewtons left over. Okay, and now we can go on to joint B. FAE, just remember, FAE, FAC is 0. FAB is 4. So here we have the 4. We write that down. Let's go back. Let's see. We're looking at joint. Oh, what joint are we looking at? Joint B. Okay. So so we have the FBD, FBE, BXBY. Okay, let's take a look at that. Now, here's this. So that'd be reaction BXBY. This force due to that link. Did they label it point R? No, they didn't. They just left it alone. Okay, but that's okay. We know what they're talking about. It's that little link to the wall. FAB, they left it alone. It's 4 kilonewtons. FBE, see, FAE and FAC are 0. So we have FAB and FDB. And what they call R, what the book calls R, which is as good of symbol as anything. Okay. Yeah. Looking back at FBE, we notice there's no displacement in the y direction. It's the same distance in the x and y, so it would be down at 45-degree angle right here. Okay. Okay, looks like we have all the information we need, and we can start doing our XYZ coordinates. So FABE is in the y direction only, 4 kilonewtons. You'll notice I have dropped the units sometimes in an equation, and I will write it out here, like so. They're doing the same thing. So watch out for that. RB sine theta, and that's in the positive y direction. So that's the y equation. Anything else in the y? No. FBE is not in the y direction. FBD is not in the y direction. And the load and the applied load, the 2 kilonewtons, is not in the y. They're all in the z. FBE has an x component. Nothing in the y. So only RB and FAB. So let's look at the x direction. We have RB and FBE in the x direction. We don't have anything else in the x direction. The other three forces are in the y or z. So FBE has to equal RB. Cosine of 45 degrees is 707, by the way. They're both the same. And so we're going to get the two are going to have to equal each other. And then finally, the z direction, the 2 kilonewtons applied, FBD going up, 1 over root 2 FBE going down, negative. So RB is going to be 4 over sine 45. You'll notice a lot of times which is going to be 1.4 times 4, 5.66. There we go. Right there. And it has, and they do have to equal. RB equals FBE. Okay. From this equation, we get this, and then from this equation, we get this result. Okay. And the positive value tells us its intention. Positive forces tell us its intention. FBD, we're drawing. The drawings are all in tension. We're showing the drawing as if everything's in tension. FBD is in compression. There we go. They tell us that. FBE is in compression. So, 0.707 FBE, well, that's sine of 40. Anyway, it's going to, this quantity here is 4 kilonewtons. So FBD has to equal 2 kilonewtons. Okay. So I will leave this one up to you guys to show that the rest of the beams result in zero forces. We've gone through a couple joints looking at the other 2 joints. You know, you guys can figure that out. Okay, frames and machines now. Here's the deal with them. Frames are designed to move, not to move. Machines have moving parts. But analysis is identical. You assume they're not moving. They're in a condition, they're in a state where they're not moving. What is the equilibrium? So even machines, you would analyze statically. Assumptions, usually 2D analysis. So joints are modeled as pin joints, not 2-force members, multi-force members. So the way to approach this one is you break it down, break the structure down into members and draw the free body diagram for each member. So we're going to start out by going through a bunch of free body diagrams. So we have this right here and a force on it. Drawing the forces on AB, we have reaction forces at A, we have forces at B, we have an applied moment. Okay. Now, the force of the joint on the left side is equal and opposite to the force of the joint on the right side. Okay. The same thing for the y component, by. So we see that in this blow up here. The effective member AB on the pin, these two. The effective member BC on the pin, these two. So these forces are associated with the right-hand member. These are the forces associated with the left-hand member. This is the force of the left on the right. This is the force of the right on the left. Okay? Which is why these things come in pair. Carefully draw your free body diagram to show this. Then you can analyze a frame or machine. Moving on, next video.